Thank you, Mas. Welcome, everybody. It's good to know that there are many people who are interested in this seminar. How can I change to the next one? Okay. So we have collected for today's seminar a number of case studies, examples of analysis of different types of dams that we will go through. We are going to look into thermal effects on deformations of dams, thermal effects from the environment, also from the casting phase, the young hardening concrete aspects. We're looking into construction stages, to failure of concrete in dam applications. We are looking to groundwater flow effects, to changing material parameters, and the last case studies that we will discuss is a seismic analysis of a concrete arch dam. But before we do that, I would like the opportunity to say a few words about TNO DIANA. So, TNO DIANA is a spin-off company of the Netherlands Organization of Applied Research, and we started our business in the year 2003, so 10 years ago. And our business is the development and the marketing and distribution of the DIANA Finite Element program. And the development of this software goes back to the mid-70s when the development of this program was initiated in the Department of Computational Mechanics of TNO. And we have always focused on the applications of civil and geotechnical engineering. So our customers are worldwide, engineering consultants, oil and gas companies, and a lot of research organizations and universities, because our focus always has been on the combination of different physical aspects and especially the nonlinear behavior of structures. So on this picture you see our office, which is located in Delft in the Netherlands, and typical of the Netherlands is that an important part of the country is located below sea level. So we are very dependent on dams and dikes. But the dams and dikes in the Netherlands are not so high. They are very long, but not so high. We will focus in this webinar mainly on big dams, large dams, as you see in many mountainous countries. So on this sheet you see an overview of different applications that we can address with the DIANA program. We can, for example, model the failure of reinforced concrete, geotechnical aspects, nonlinear soil and rock behavior, geomechanical applications in oil and gas, masonry, historical buildings, dams and dikes, of course, earthquake aspects, extreme temperature loading such as fire analysis, etc. But the interesting thing of application of DIANA on dams is that many aspects come together here. We have, of course, the dam structure itself, which is interacting with a soil or rock foundation. There is interaction with the fluid, with the water, especially in dynamic analysis. This is very important, but also the water can can flow through the soil foundation, and this aspect can be considered in the analysis, and also the thermal effects, because the large size, the large dimensions of the dam can be significant. So let's start now at the first application, which is about a concrete dam under which we will look into a thermostress analysis. This is a case study that we have presented for a 9th benchmark workshop on numerical analysis, which has been organized a couple of years ago in St. Petersburg. And the purpose of this benchmark was to identify and predict displacements of the structures as results of two types of loadings. First is the hydrostatic loading, the loading from the water on the dam, and the other loading aspect that was considered here is the environment temperature. And the purpose of the benchmark is to predict monitored or displacements on this dam. So here you see a schematic cross-section of the dam, on which on one side you see the water level, which varies with time. The temperature of the water was assumed to be constant, and on the remaining cross-section of the dam, external temperatures, which were of course the environment temperature changing every day of the year, were considered. And the benchmark formulators defined 5 different load cases. The first one was defined as a reference situation, and you see that the water level was one of the parameters that was varied, and the external temperature the other parameter that was varied. So how to deal such conditions in a finite element analysis? In fact, we need to consider 2 physical phenomena. First is the heat transfer, in which we need to look into energy balance of the system. We calculate the temperature field in the dam and then apply that as a loading condition, a boundary condition to the dam structure. So we account for the thermal expansion. That means we have a thermal expansion strain prescribed in the elements, which we will balance with the boundary conditions and the external loads that are applied, such as the hydrostatic load and the weight load. So here you see a cross-section of the dam, in which part of the dam has been removed. So this irregular cross-section are just the different elements. And on the top 5 figures that you see here, we have the results of the heat flow analysis, which is a steady state heat flow analysis for the different loading conditions. On this side here you see the level of the water with the low temperature, 5 degrees for the water, and on the other faces of the dam you see the environment temperature, which varies with time. And with this steady state heat analysis, we can calculate in every element of the structure the temperatures. And these temperatures are in a follow-on analysis considered as a loading in a stress analysis, in which we calculate the displacements, which you see here in these for the corresponding loading conditions. And here we have for 2 reference points, this is the crest of the dam, compared the calculated displacements with the measurements. So the measurements are the target results. You see quite some difference, and we have done that for 2 different conditions, 2 stiffness parameters, 2 stiffness conditions for the rock foundation. There was not very clear what were the conditions, and you see that it doesn't give a big difference, but on some conditions the difference is more significant. And here you see the same for a point on the upstream side face of the dam. So second application that I want to discuss with you is also heat stress analysis, in which we look to Storfinn-Horsen Dam. It's a dam in Sweden. This is a case that we have done together with Vattenfall. It's a monolith, a dam which is a buttress dam, so we have a slab with a lot of buttresses, and we looked only to one of these buttresses, one of these monoliths, which is here depicted in more detail. You see the dimensions, the water side on this face. And of course this is a concrete structure with reinforcement details that are displayed here. But this is a model in which we have looked to the cracking behavior, the failure of the concrete. And we have done that with defining a total strain crack model for the concrete. You do that by defining a uniaxial relation for the concrete. Here you see the uniaxial strain axis and the stresses, and the material behavior can be defined by compression curve, here with Torrenfeld type, or tension curve, exponential softening here. This is the crack energy that can be taken by the concrete. So every load step, every integration point, the strains are, the principal strains are calculated in every integration point, and we calculate the corresponding stresses in those directions. And the main loading here were variations in temperature. In Scandinavia we have quite a variation in temperature in winter and in summer, and you see on the free face of the dam, in winter there will be shrinkage because of cold temperature, whereas in summer there will be thermal expansion. And what is the effect of these thermal strains on the crack behavior of the dam? So we have done a transient analysis in which we looked at the behavior over a period of 20 years. And first, already after a few years, there were crack noticed in the dams, which we could reproduce with the analysis very nicely. And at that time, after 5 years, an isolation wall was constructed on this location, just to protect the dam for these temperature changes. But what you see is, because of this isolation wall, the temperature expansion was more located on the outer part of the dam. So instead of reducing the thermal expansion effect, it more localized the effect here around this part. So after 20 years there were even more cracks predicted than we found in the situation after 5 years. The next tutorial or example that I want to show you is again a benchmark that we did for this ICOLD workshop, this time 1 year later in Paris. It's a stage construction analysis of an arch dam in which we want to look for the reasons to predict the cracking immediately after construction. So not cracks as a result of the hydrostatic loading of the dam, but just from the hardening of the concrete in the initial phase. And we do that by simulating the different construction phases of the dam. Here you see in the different blocks here the different phases that were identified. In total 155 phases in which the model, the dam was composed. We did the following assumptions in the models. We disregarded, neglected the joints. We restricted ourselves to linear elastic material behavior, but looked into time-dependent behavior. So stiffness and tensile strength that are function of the maturity and the thermal effects which vary with time during this early age of the concrete. And each casting phase, so 155 in total, was modeled with only one layer of elements. So you have seen this picture before, but this is slightly different because what we do here for this type of analysis is, again, we do first a thermal analysis in which we calculate the temperature development in each of the 155 phases before we do a stress analysis. But here we do not only transform the temperatures for the thermal expansion as input in the stress analysis, but also define and calculate the conditions for the creep and shrinkage, which are effects that are dependent on the maturity and the equivalent age of the concrete, which can be derived and defined by the temperature that is developed during the casting process of the concrete. How does that work? We do a staggered analysis. First we do a heat flow analysis. We calculate the temperatures, and in the conversion we will calculate from the time temperature curves in every point of the model also the degree of reaction and the equivalent age of the material. And these three parameters are the input in a structural analysis. Also nice to explain to you in this phase, in this sheet, is that DIANA uses always in a heat flow analysis elements which are one order lower in their interpolation function than in a stress analysis. And we do that because that way we get the most accurate results, and we can avoid fluctuations in the stress fields. Because in a thermal analysis we calculate temperature fields. Temperature fields are directly related to thermal expansions, to strains, and strains are always one order lower than the displacements that we use as basic entities in displacement or stress analysis, in the structure analysis. So for this we just interpolate the temperatures and degrees of reactions from the corner nodes to the mid nodes, and then can do the structural analysis. So let's look in what this means, this degree of reaction. In degree of reaction we look to the heat that is generated into a certain time in relation to the total heat that can be generated by the concrete during the hardening phase. And the same way we can define equivalent age. We have two types of equivalent age, a Arrhenius type and a Sol definition. In this analysis we also considered creep, so therefore we defined double power law definition. You see the Young's modulus here in this version, which is a function of time or function of equivalent age. And we did a linear elastic analysis, but we compared the principal stresses, as you see here, with the tensile strength. Tensile strength, which is a material parameter, which will develop with the hardening of the concrete, so it's a function of time or a function of maturity. And the relation of this we define as a crack indicator. So when the crack indicator is larger than 1, everything is safe, and when it is 1 or smaller than 1, you may expect cracks in the concrete. Other aspects that we consider in this analysis is the shrinkage. Of course we have the thermal shrinkage as a result of temperature changes, but we also considered here autogeneous shrinkage, just because of the concrete reducing size as function of time. So considering all these aspects, we need following material input. The heat development of the concrete under adiabatic conditions. So that can be done by this curve. This is the heat temperature increase as function of time here in days. It's a monotonous increasing curve which goes to a maximum value. which correspond with the total heat that can be generated. And same way we have also a curve for the Young's modulus, the development of the Young's modulus as function of time, and also the tensile strength. So instead of a single parameter, we define a curve. And then we can calculate for the different construction phases as function of time the temperature distribution. Here you see that this huge dam, only half of the dam was considered in this model because of symmetry conditions. And here the colored parts, that is the dam that was constructed at this date of 14th May. You see the dam was built in a relatively short period, a little bit more than 6 months. And the colors represent the temperature at this date inside the dam. So the outside also varies, the outside, because that is defined, the outside temperature, by the environment temperature, whereas the internal of the dam usually shows higher temperature because of the heat generation. And with time, this heat in the dam will reduce because the heat will flow out of the model to the environment. And then after this heat phase, we can calculate for every time step also the principal stresses based on this linear analysis, which you see here, same time color scale, varying from very low level stresses to tensile stresses up to 6 megapascal. At the second half of the construction phase of the dam until some months after the dam. And you see that because of the development of the temperature and the environment, changing environment temperatures, there's still variations in the stress after the construction has been finished. And this phase for the same in this sheet, for the same phases, you see the utilization factor of the distribution. So the red areas are the areas where cracks can be expected, which the stress is the principal stress is higher than the tensile strength. So conclusion of this analysis, when I go back, is that this dam was probably constructed so fast that the temperature could not redistribute good enough, and therefore, then as a result, the concrete was cracked already significantly before the end of construction, or just after construction, before operation. The next case is a complete different type of dam. It's a Rockfill dam. A Rockfill dam, which we look at the construction stage, and especially on damage which was noticed in this dam in the concrete slab. That was another benchmark which we did for the ICOLT, in fact on the same session in Paris. And what you see here is the different construction phases of the dam body, which we modeled with chem clay type material model, because chem clay type is a very nice model that can both describe shear failure as well as compressive failure of the granular material. And you see the different phases of the construction. On one side of this construction, of this Rockfill body, a concrete slab was applied, and this slab consists of different slices which are connected with joints. For the purpose of this model, we defined the slab with shell elements as displayed here. So they have possibility of rotations and bending around the edges, and on the interfaces, which are illustrated here with the red lines, we have defined interface elements. And these interface elements are especially for interaction between shell elements. So they do not only hinge around the connections, but also consider that when it is hinging on one side, the hinge point is shifting to the top face of the slab, whereas it is hinging on the other side, the hinging point is moving to the lower edge of the slab. These interface elements can also describe shear and opening and closing. So in this analysis we considered a lot of construction phases. First phase we only applied the dead weight and looked only to the foundation, and then we constructed the concrete body of the rockfill body of the dam in 5 phases. And when half of the rockfill body was constructed, also the concrete slab up to this altitude was installed. And then in the next phases the concrete body was completed, followed by completion of the concrete slab. That was what we call the end of construction of the dam, and from then on we applied a water load, a hydrostatic load with increasing water level in 5 phases up to full impoundment in stage number 16. So here again we see the different phases of construction of the rockfill body, and here we see the crack development with different levels of impounding of the reservoir. That brings us to the next example, which is in which we are going to look into the interaction of water and the dam, and especially water in the dam. So the type of dam we are talking here about is an earthfill dam. And the type of analysis we use for this is a staggered analysis, in which we first do a groundwater flow analysis, and when we have calculated the pore pressure distribution in the dam, the pore pressure is result of the water pressure, we will calculate the stresses in the dams and the related deformations. So this is again multi-physics approach, in which we do first a groundwater flow analysis, the calculated pore pressures, the excess pore pressures will be applied as a load to the dam body, and then we can calculate the stresses and displacements. In this type of analysis, the volumetric deformations, which will affect the porosity, are not considered. So this is a one-way coupling. And the type of dam here, the earthfill dam, uses here very porous earth with a clay core that you see in the middle and a cut-off wall. So how does that work? We first do a potential flow analysis or a groundwater flow analysis, in which we call the hydraulic heads, and then as a gradient, here you see there are some gradients in the hydraulic head, some variations in color under the cut-off wall where the water flows under the dam, and also strong gradients here in the clay body where the permeability is relatively low. And then we can calculate as a gradient from this hydraulic heads the fluxes, which are displayed here with arrows. When the arrows are larger, they get a color. Here you see the very small level of flow in the clay body because of the low permeability, but the water tries to flow around the clay body, around the cut-off wall, here to the free body, but because the permeability here is higher than in the foundation, there will be some seepage here out of the body. From this hydraulic head we can derive the pressure head, which is just the hydraulic head corrected for the gravity gradient of the water. And where the pressure head is equal to 0, we find the phreatic line, which is in fact the water surface in the dam. That means that this part of the dam here is below, water is fully saturated, whereas this part of the dam is not saturated. That brings us to a small animation that you see here. You see the pressure head with the phreatic line. On the left side of the dam, the water level is going up and down, and we see with this seepage analysis, with this groundwater flow analysis, we can calculate the water level in the dam at every time stage. And in the subsequent analysis, the stress analysis, this water pressure is applied as a load in a stress analysis, which we calculate the effective stresses and the deformations. So because of the increasing water level on the left side, you see that the dam is pushed aside. One variation of this type of seepage analysis is the following one, where we do not a staggered approach, but we do a fully coupled flow stress analysis. So this picture is again very similar to the picture I've shown to you 3 or 4 sheets earlier, but there was a cross here in which we said there is only a one-way coupling. In this way we use the volumetric deformations, so the compaction of the elements, and the effect that that has on the changes of the porosity or the permeability, which affect the flow, the groundwater flow. So the groundwater flow produces pore pressures, which are input in the stress analysis, and the deformations have effect on the changing porosity, which have input in the flow analysis. And both these two physical aspects are in a fully coupled analysis solved at the same time. So we make one set of equations and solve that in a fully coupled way. So also the interaction between both aspects in both directions are considered. What we see here is the same dam with varying water level. But here the water content in the clay, it penetrates in the clay body, and when the water level is reduced on this side, we see that there's still a water level remaining in the clay body, and it takes some time before it can flow out. Now let's have a look about changing material properties, and when we're talking about concrete structures, the swelling of concrete as a result of alkali-silica reactions is an aspect that we have considered in this benchmark study in 2011, ICOL benchmark in Valencia. So the topic of this benchmark is the Kariba Dam in South Africa. You see the model here, and the aim was to predict displacements and check the effect of stress distribution in the dam as results of these changing properties of the dam as a result of AAR or ASR. And what we did in this model is that we applied joints between the different columns of concrete, such as they are defined in the construction phase of the dam, which you see here. So these interface elements are in fact elements that are very stiff in compaction, but will open when the elements are under tension. So on this figure here you see the same dam with a hydrostatic load that is considered. And first we did a analysis in which we applied this nonlinear behavior, but we did not yet apply the changing properties. So we want to have a reference situation. We calculated the results without swelling. And here you see the calculated tractions or stresses in the interface elements. So red means the stress is equal to 0, and blue means there is a compressive stress. So this is at the end of construction. All the columns are there, and you see there is hardly any stress. In the circumferential direction, this is of course before loading, before the hydrostatic load is approached. In the same condition, the same time step, you see here the relative displacements. So where the interfaces are closed, can transfer compressive stresses. The displacements will be negative, very slightly negative or close to 0. That's dark blue. And when they are opened, there will be an opening. And you can see here that the opening is green, is around 3 millimeters up to 7 millimeters at the maximum opening that you find here locally. So that means that these columns after construction are bending outwards upstream. So here we calculate the so you see the stresses on the downstream phase and the upstream phase of the dam. No swelling considered, and we have displayed stresses with principal stresses. That means with crosses. They are on the outside of the dam, so there's no stress in the normal direction to the face of the dam. And you see here that all the stresses are in vertical direction. Because in the circumferential direction there are these joints which prevent that circumferential stresses can be built up. And you also see that all the vertical stresses at the interaction with the foundation here, the blue here, are almost 0. But on the upstream phase there are high concentrations of the vertical stress. That's because the whole dam is leaning upstream. And these figures is the same dam, same material properties, but with hydrostatic loading. And you see very nice that here there is a strong compressive circumferential stresses, which nicely illustrates the arch working in the dam. So now we are going to account for the swelling, the ASR, and we don't have a specific model in DIANA available for describing this swelling behavior, but we misused the thermal expansion functionality. And this ASR swelling works the strongest, works in an anisotropic way. It works the strongest in the direction normal to the highest compressive stresses. So they are in the vertical direction. So we defined a swelling which was a little bit stronger in the horizontal direction, thermal expansion coefficient that was higher in the horizontal direction than in the vertical direction. And then we defined a function of time of this swelling according to Larive function that you see here, that is this red function, which we calibrated as good as possible on some displacement measurements that were provided by the benchmark formulators. Here's one point. This is in the center of the crest in which there was a construction. These measurements, which we didn't consider this construction in the analysis, so we have neglected these series of measurements. This is the leveling, so the vertical displacement as function of time of different locations. And here you see the radial displacement of the crest. And the challenge of the benchmark was the measurements were provided up to 1995 to give predictions of the further displacements in the following 15 years. So therefore we have used this Larive curve. And we could calculate predictions very well. During the benchmark session, this was compared with experiments and gave good agreement. And yeah, here you see the stresses again in the dam phases, considering in the model where the anisotropic swelling was considered. That brings us to the last case study, which is a seismic analysis of a concrete arch dam. So in DIANA we have different types of dynamic analysis that we can use to assess the behavior under dynamic conditions or earthquake conditions of a dam. We need to distinguish between linear analysis and nonlinear analysis, because if we have linear analysis, we have the option to do the analysis either in the time domain or in the frequency domain. And the frequency domain has some advantages because usually it is very efficient and you can define some damping parameters as function of frequency. For example, compressibility of the fluid or the bottom absorption of fluid in a dam, which is important. On the other hand, when you want to consider the nonlinear behavior of the structure, you cannot use frequency analysis and you should use transient analysis, so analysis in the time domain. Very recently we have developed a new analysis procedure, which is hybrid frequency time domain, in which we can combine both aspects, the advantages of frequency analysis and nonlinear analysis. So for example, the compressibility of the fluid in a dynamic analysis or the bottom absorption in combination with nonlinear failure behavior of the concrete. But in this case study, we will do a transient analysis of a concrete arch dam. And the dam we will look into is the Luzone Dam in Switzerland, for which the model was provided to us by Stuckey. This is a dam of 225 meters high, which we will look what is the effect on an earthquake analysis of 6 to 6.5 on Richter scale. And we will look not only to the dam itself, but also look on the effect of the fluid on the structure, where to the structure, to the concrete dam, we will define a concrete cracking material model so that we can look and study the effect of the failure of concrete under such earthquake loading. Another aspect is that in this case study we will show the effect and the development of dynamic pressures on the dam. So this is the finite element model of the dam. So the dam is modeled with solid elements. In yellow you see the rock foundation. Here it's the same model, but the rock is transparent so that you can see how the dam is embedded in the rock, and you see that we have modeled the fluid domain also with fluid elements to account for the fluid interaction. Here you see the same dam from the other side, with and without fluid. And the first step in this analysis, in such a dynamic analysis, is that we need to make a decision and we need to calculate how we are going to apply the damping effect. Therefore, we start with a simple eigenvalue analysis in which we do not consider the mass in the foundation, and we also do not consider the effect of the fluid. But we calculate a number of eigenvalues of the dam considering the stiffness of the foundation, in which we calculate the different eigenmodes and the effective masses related to these eigenmodes for the main directions, the x direction, y direction and z direction, which are the sideward direction, the stream direction and the gravity direction respectively. And then DIANA output also the percentage of energy in each of these directions, of how much energy of the system is represented by these eigenmodes. And what you see here is that, for example, here we have a mode in the red frame in which you see a very big step in the cumulative percentage of energy of the dam, from 15 to 82%, which is very dominant mode, as we say. You see here also in the y direction we have selected two dominant modes, and the same in the z direction. So we come to these modes later on, but what you see is that if we look to the first 15 modes in the frequency range from 1.8 hertz up to 6.5 hertz, we cover roughly up to 90% of the energy in the system. And this energy range, this range of frequencies, is the range that we want to apply. We define a damping ratio of 5%. From this condition, the software calculates the Rayleigh coefficients that we will apply, alpha and beta, in the transient analysis. So the four dominant modes that I've highlighted on the previous sheet are depicted here. You see them with the frequency and their corresponding shapes. So before we go to the transient analysis, we have calculated now the Rayleigh damping parameters. We need to define some properties for the fluid. We need to define the free surface pressure, and we need to define a hydrostatic load on the dam. And of course we need to define the time function, the acceleration function for the earthquake loading, which you see here. It's a function of time, the acceleration, the velocity, and the displacement in the stream direction only in this case. I said we also will in this case apply a total strain crack model to the dam body, which is schematized here in this picture. You see here the crack strain and here the crack stress. So initially there's linear elastic behavior up to tensile strength that is reached, and then the concrete will soften according to this curve. But when in the meantime this is cyclic loading, this is earthquake, an unloading, it will not follow the same curve, but it will directly unload towards the origin, and then in the compression follow the compressive curve. So when we look now as function of time, we start the earthquake at 100 seconds, so that's on this location. The number of cracks and status of the cracks in the model, we see here with the pink line that there are some peaks in which very short time the number of cracks increases very strongly and then immediately reduces to a low level. And then here we have close cracks, which gives a function of time. We will look and three different crack patterns on three different time steps in the following functions, as you see here. So these are the major pulses that are identified at these time steps. So here, for example, this time step, we see the displacement, we see the crack distribution, the crack strains, the areas where the crack is open. It's an important part of the dam, and at the same time we can calculate the hydrodynamic fluid pressure, in which we see that the highest the concentration of the dynamic fluid pressure is on the center top of the dam. And you could do that for different time steps. So that brings me to the end of this last case study. I hope it has given you more insight on different type of analysis, different physical loading conditions that can be considered with the DIANA program. And I hope this was meeting your expectations. I give back to Maas.
Thank you, Herdian. It was very informative, and I hope we received the same feedback from our audiences. I would like to take advantage of this session and highlight two of our upcoming technical courses, which we hold them in our headquarters in Delft. The first one will be about the reinforced concrete in September, and after that we will have another technical course about the geotechnical applications using the DIANA program, and that will be in October. So feel free to visit our website. There will be a full program about these two courses, and you can register to them based on the relevant topics and relevant days. So right now we will be available to answer your questions. Please feel free to type your questions. If you want to have a live chat, please let me know. I can release your microphone. Otherwise, you can always contact us through the email, or you can simply reply to my invitation email that you received for this session. So thank you very much for your time, and we will be available to answer your questions.